Finite element analysis is a useful tool for understanding different phenomena. Today, I will show you the influence of curling on the strength of connections with one bolt. Good morning, good afternoon, and good evening to everybody. My name is Primoz Moze. I come from University of Ljubljana, and this work was performed by Matej Toporis for his master thesis. Single bolt connections can fail in different ways. They can fail in splitting failures, where the part of net cross-section yields and allows rotation of the plate, splitting the plate into two parts. Shear failure pulls out the bolt, creating two shear failures in the plate, while curling failure is associated with thinner plates that tend to bend out of plane. One of possible failures is also net cross-section failure. The curling failure is generally not considered in the design checks for practitioners. However, there are different proposals in the literature that address this problem. One of them being proposed by Salih and authors that is written on the slide. The objectives of this study was to understand the mechanics of curling addressed by finite element analysis, to develop simple analytical mechanical model that could provide a reduction of the bearing resistance that considered the curling phenomena. Numerical analysis were performed in Abacus using two material models, one for mild steel S235 and one for high strength steel S690. Two types of finite element analysis were performed. The first one for determining the strength of plating bearing. This was geometric and material nonlinear analysis with and without imperfections, and the other type of analysis was linear buckling analysis with different boundary conditions to determine the form shape and plate slenderness due to bearing at bolt hole. Model to determine the strength was assembled of plate element that was meshed with solid element, bolt that was presented by cylinder, rigid cylinder, where the contact between the plate and the bolt was defined. The displacement was applied in the reference point and the cylinder was fully supported. The model for linear buckling analysis was a little bit simpler. Plate bolt was replaced by different boundary conditions. There were three types of boundary conditions considered. The analysis with these types were noted as buck 1, buck 2, and buck 3. In buck 1, only a middle line in the wall hole, the nodes were restrained in the X direction. With buck 2, the whole surface of the wall hole was supported in X direction, while in buck 3, the nodes on the wall hole were supported in polar coordinate system. The initial imperfections were considered as the buckling shapes that resembled of curling failure and were introduced by two different amplitudes, end distance over 300 and end distance over 200. Several parameters were included in the parametric numerical analysis. The bolt diameter was kept constant. This was 20 millimeters, while the thickness increased from 3 millimeters to 6 millimeters. Then the end distance and the edge distance changed in steps from 1.2 of the hole diameter to 4 times hole diameter. Two different material models were used and two different amplitudes of imperfections were used. On the slide, you can see the principal stresses, minimal principal stresses and maximal principal stresses when the bolt bears to the plate. The plate near the bolt is exposed to high compression stresses that yield and tend to become unstable, and therefore it can buckle out of plane, while the tension stresses in this direction tend to stabilize the edge of the plate. Curling failures were observed also in the analysis without imperfections, with thinner plates, that is with 3 and 4 millimeter plates with relatively large end distance, so distance being equal or larger to 2.2 of hole diameter. The curling failure were more pronounced for material model with high strength steel. The edge distance E2, this is basically the width of the plate, had only a negligible influence on the reduction of bearing strength due to curling. The graph presents load displacement curves for connection with geometry and distance equaling 2.5 d0 and edge distance equaling 2 d0. The two types of curves are shown for high strength steel and for mild steel. The black curve shows the analysis where the curling was restrained, while the red curve presents the analysis without imperfections but curling developed, while the blue and the red curve present the analysis with imperfection. You may see that significant reduction of bearing resistance was observed due to curling, and that the initial imperfection has a significant influence on the reduction of bearing resistance. Because the curling is associated with compression stresses, we decided to use Eurocode approach to determine relative slenderness of the plate due to bolt bearing, and further on to determine the reduction factor. The relative plate slenderness due to bearing at bolt hole is defined and calculated as a square root of ratio of the bearing resistance where the curling is restrained, and in the denominator the elastic critical force causing the curling buckling moment, which was obtained by linear buckling analysis. The reduction of resistance is a ratio between the bearing resistance, which accounts for the reduction of the curling obtained by geometrical nonlinear analysis with imperfections. On the curve, these are these points, and divided by the bearing resistance where the curling is restrained. So on the curve, this would be this point on the top. If we plot the results of the numerical parametric study for both steel grades with different boundary conditions, we see that we can observe some trend in the results. So on the x-axis is slenderness, on the y-axis is a reduction factor. We can observe that approximately to 0.2 slenderness, there is more or less no reduction, and then a steep drop in the resistance. We also can observe that boundary conditions with BAC 1 are more scattered, while BAC 2 and BAC 3 boundary conditions give very similar results. So therefore, in the further analysis, we used the boundary condition BAC 2. Determination of slenderness and reduction factor by complex finament analysis is not suitable for practitioners. Therefore, we developed an analytical model which was based on the results of parametrical study. The slenderness can be determined using a simple analytical model of the cantilever subjected to axial compression, where the length of the cantilever and effective cross-section is determined on the results of parametric study. The length of the cantilever was defined as the length where the compression stress is approximately uniform, while the effective width equals to 0.35 of end distance, but not being more than the net width of the plate. We can calculate analytical slenderness as a square root of the ratio between the resistance. Resistance is defined with as a minimum between the bearing resistance and net cross-section resistance, and divided by Euler buckling force for the cantilever. For the bearing resistance, we used a model that is included in the new version of Eurocode, which is simpler than the previous one and is written on this slide. We use this model because the results were much better fitted to the results of analytical model, were much better fitted to the numerical results with this model as with any other model that we tried. On this diagram, we compare the numerically determined slenderness and the slenderness determined by analytical model. We can see that analytically determined slenderness is always higher than the numerical one, and that the scatter of the results is not that large. So we assume that this our analytical model is fairly good. In the next step, we plot the results of numerical parametric study versus relative slenderness. And we can observe some trends that can be very easily described by some linear function. So there is no reduction up to 0.2 slenderness, and then a steep reduction for two different steel types. Because the reduction is very steep, it is more appropriate to provide some limits where the curling phenomena does not develop. So by simple derivation, assuming that slenderness is smaller than 0.2, we can arrive to the very simple limit, which says that if a ratio between end distance and thickness is smaller than 8.5 for S235 or 6.4 for S690, there is no reduction in the bearing resistance due to the curling phenomena. Our model was also tested against test results that were performed by Rex and Easterling, and they observed several curling failures on single bolt connections, and by applying our method, we can see that the points move more to the safe line, to the safe side compared to the calculations according to Eurocode for steel joints. In this presentation, I showed the influence of curling failure on the bearing resistance of single bolt connections that were studied by parametric numerical analysis, which was the basis for the derivation and calibration of a simple analytical model used to calculate the relative slenderness and the reduction of the bearing resistance due to curling phenomena. These are the references that were used. Thank you for paying attention and enjoy the rest of the conference. Goodbye.